Hey everybody, welcome back. Let's do a triple integral in spherical coordinates. So let's say we've got the triple integral over some solid q of y squared dv, where q is the solid hemisphere, x squared plus y squared plus z squared is less than or equal to 9, and y is strictly non-negative. So that's going to give us this portion right here. So the first thing that we want to do is describe rho, phi, and theta relative to our picture and our solid. So this is the solid Q. And let's see here. So rho is going to go from 0 to 3. So rho goes from 0 to a maximum value of 3. And so phi, that's the angle measured from the positive z-axis. So we do this in the way that you would in a multivariable calculus class. I know that in a lot of physics classes, they'll interchange the roles of phi and theta, but let's do this the multivariable calculus way. So we're going to measure phi from the positive z-axis. So phi will go from 0 to a max phi of pi. So phi goes from 0 to pi. And then theta is the angle measured from the positive x-axis. So theta will go from 0 all the way around, if I were to sort of extend that, all the way out to pi. So theta goes from 0 to pi. Okay, so phi is measured this way, and theta is measured this way, sort of around, sort of like its belt angle in a sense. So that's really nice. So what else do we know in spherical coordinates? Well, we know that x squared plus y squared plus z squared is equal to rho squared by the Pythagorean theorem. And here we know by the Jacobian that dv is equal to rho squared sine of phi d rho d phi d theta. So that's pretty helpful. Okay, so let's see if we can describe this in spherical. It might be also pretty nice to mention the following, just for context. So let's call this a recall. So remember in spherical coordinates that x is equal to rho sine of phi cosine of theta. Now y is equal to rho sine of phi sine of theta, and then z is equal to rho cosine of phi. So keep that in mind because we're going to need y squared here. So we've got dv here, that'll take care of this, and then y squared will go here. Okay, so let's go ahead and fill this in and start to solve. So the original triple integral, which would have been an absolute nightmare to solve in Cartesian coordinates, is given by this much nicer form in spherical coordinates. So let's say the inside integral is rho, and we said rho goes from 0 to 3. Let's say the middle integral is phi. Phi goes from 0 to pi. And the outer integral here, let's say that's theta. And theta goes from 0 to pi as well. Okay, rho, phi, theta. So I need y squared, right? So y squared. Okay, so here's y squared. And then we need dv. So be careful because dv, so this is rho squared sine of phi, and then in order, d rho, d phi, d theta. Okay, so that's the setup for our integral in spherical coordinates. Let's go ahead and maybe square this and then combine with these and see if we can make this a little bit nicer. and then we'll carefully calculate. Okay, so I've got rho squared times rho squared. That's going to be rho to the fourth. So rho to the fourth. I've got sine squared of phi, right? Sine squared of phi times sine of phi. That's going to be sine cubed of phi. And then I've got sine squared of theta. So sine squared of theta. And then this is d rho, d phi, d theta. Okay, so that seems pretty good. And we can start to split this up because, for example, with the rho integral, so there's no phi or theta dependence in the rho integral. There's no mention of phi or theta. So I can start to factor this out. Okay, so in front of the rho integral, I can factor out d phi, sine cubed of phi. That can be factored out in front. And then for thetas, I can factor sine squared of theta d theta in front of both the rho integral and then the phi integral and bring it out here. So that's going to give me the product of three integrals. So on the very outside will be the theta integral. So that's going to be sine squared of theta d theta. And this will be times, so the integral from 0 to pi, of sine cubed of phi d phi. And then the integral from 0 to 3 of rho to the fourth d rho. Okay, so these are pretty typical single variable calculus style integrals. You may have encountered things like this in Calc 2. And this is very much a Calculus 1 style integral. Okay, so let's start to think about what technique is appropriate. So for this one, this is raised to an even power. So I want to think about the power reducing formula. This just comes from the double angle formula for cosine. So you just want to remember that sine squared of theta is equal to 1 minus the cosine of a double angle, or 2 times theta, over 2. So that'll help us solve this. So I've got 1 minus the cosine of a double angle, and I'm going to write over 2 like this in front of the integral. That's going from 0 to pi. And there's d theta. Now for this, I'm going to rewrite this. This is to an odd power, right? So if this is to an odd power, it might be smart to write this as sine squared of phi times sine to the first. Together, that's still sine cubed. And our goal is maybe to use a Pythagorean identity here, which leads towards a U substitution. Okay, good. So I'm happy about this. Maybe I'll leave this right here. We could integrate that just fine. I think it'd be better to write it like that. There we go. Now here, by Pythagorean identity, we know that sine squared of phi is 1 minus the cosine squared of phi. So maybe I'll write that. So just remember that sine squared of phi plus cosine squared of phi is equal to 1 for all angles phi. Okay, so now I'm going to carry through with a substitution here. So let's do that. We can change our bounds, and then I'll start to integrate maybe all three at the same time. So for the middle integral, so by substitution, let's say u is equal to the cosine of phi. Now we know the derivative of cosine is minus sine, or negative 1 times sine. I'm going to write it like this in a very particular way here. So I'm going to multiply the minus, so it's over here. Going to remember to get new bounds. And since this is multivariable calculus, maybe we can do this all at once, right? So this is going to be 1 minus u squared. This right here, that's going to be minus du. When I change my bounds, this is going to go from 1 to minus 1. And then because of the minus, I can flip the order. So that goes from minus 1 to 1 of 1 minus u squared du. And now let's integrate everything at the same time. Okay, so that looks nice. Okay, so I do hope that made sense. Okay, so for this integral, the antiderivative of 1, so this is theta minus 1/2 sine of 2 theta from 0 to pi. This will be times. That's u minus u cubed over 3 from minus 1 to 1. You could also use the fact that this is an even function on a symmetric interval and write this is 2 times the integral from 0 to 1. That's your choice. Here, this is going to be rho to the 5th over 5 from 0 to 3. So that was just the power rule. And let's see how we do here. So I noticed that both of these will vanish at 0. And I actually noticed that this will vanish if I plug in pi because I'll have sine of 2 pi, which is 0. So I only get a contribution here at pi because I'll have pi minus 0 minus, well, 0 minus 0. So that's not too bad. So that's just going to give me a pi over 2. Now here, this is going to be 1 minus a third. And you're going to notice maybe some double negatives in a moment. So 1 minus a third minus 1 plus a third. So it's essentially this plus itself when you distribute the minus. And then here, this is going to give me a 3 to the 5th over 5. So I think that gives us a 243 right here. Okay, so I've got a pi over 2. This is 2/3 plus 2/3. That's 4/3. And what else do we have here? So this looks like a, what was that, 243? Or 162. That's 162. I think I was thinking ahead. So I think that's 162. Yeah, that's right. That makes sense. Okay, so we've got 3 to the 4th times 3, which is equal to 81 times 3. And that, oh, that is 243. Look at that. Oops. Mistake of the day. There you go. Okay, so how about 243 as promised? So 243, that's over 5. And so altogether, we get 162 pi over 5. There we go. Did you catch that? I bet you did. Okay, cool problem. Very, very, very useful technique.